Swayam Prabha. Digital India. Educated India.
I must tell you that it's been a real pleasure to come and give these lectures, because you guys ask a lot of good questions. So that makes anybody giving lectures happy. Um, Last thing I want is people dozing and not paying attention. That's the good news is that you're asking questions. Bad news is that means I can't cover many things. But that's okay. I don't want to cover too many things because the material is there. I would rather take your questions and have good discussion. And what that means is that I may not cover everything that you're interested in. If you later have questions, you can always send me an email. If it's difficult to find a one-on-one in-person meeting, we can at least have a Zoom meeting. Okay, some of you have said, and we can even have in-depth meetings that involves you, your advisor, and me. We can discuss. Okay, that's sort of one of the main reason why really I signed on to this is exchange some things that I've learned over the years, and also look for opportunities to just exchange ideas, possibly even collaborate, etc. And also if you need some other connections elsewhere, and since I'm the editor, I'm quite familiar with different people working. So I may not know this, but I will be able to put you in touch with other groups or faculty who are doing similar stuff. Okay, so what we're talking about in the next few slides is Euler-Lagrange methods. Okay, in this set of slides, I'm going to talk about basics. I'm mostly going to talk only about basics. First of all, I want to say the filter with L, there is a filter with, when you use the Euler-Lagrange governing equation, whether you have filtered or not, once you write and once you're solving a certain fluid, you have filtered. In other words, you have implicitly filtered. The answer that you're getting is only filtered velocity. Okay, that's what you're solving for. And what that filter size is, I would say, maybe 2 times your grid size. Okay, typically it's little more than your grid size is the implicit filter. What you've done is implicit filter. Okay, so you're solving for UC, which is the average fluid velocity at the grid point, average pressure, and so on. So that's the first bullet, which is continuous phase is filtered. And the continuous phase is being solved in an Eulerian frame. Okay, and that you can solve everywhere, including the space occupied by the particles. And if the space occupied by the particles is large, then you would have to explicitly use phi c, volume fraction of the fluid will appear, because you have to take care of the fact that your fluid is not over the entire cell, it's only over the fraction of the cell. And in this approach, of course, Lagrangian particles are being tracked. Since the flow around the particles are not resolved, you need a drag law, etc. And this is where I was saying these drag laws, etc. are in excellent shape when your particle is really small. Even though the particles are point particles, in other words, they don't have any size as far as fluid is concerned. If you use DEM, discrete element method, collision between particles, etc., suddenly you will say, oh, my particle is of this size, and you can use to detect collisions, but otherwise your particle is point. Now, what are the advantages of Euler-Lagrange? Well, no need to resolve the particle. That's the biggest advantage, because a particle resolved simulation, which we saw in the previous lecture, is painful. I mean, as the particle moves around, you have to move the grid or use immersed boundary. Some such nasty technique you have to use, okay? And also you can only take care of limited numbers. So the biggest advantage is that no need to resolve the particles, no need to apply no slip, no penetration, all those boundary conditions. So your numerical approach becomes much easier in a way, okay? And the continuous phase is solved over the entire domain. This I have made already. You can consider particles of different sizes, okay? So in Euler you have to each particle size you will have to bin it. If you are polydispersed, here you can just throw a few million particles ranging from anywhere from half a micron to 20 micron. Every size is there, okay? So it's statistically more reflective of a polydispersion, and you can use those sizes, choose those sizes exactly to fit whatever your experimental needs are, okay, whatever you use, okay. And also this is the fourth bullet, is because Lagrangian, if the Stokes number is large and different particles inside a cell going to come from some different eddies, they can have different velocities. There is no restriction. So these are good things in a Euler-Lagrange. Rotation motion of the particle can be tracked, okay. So this may be important for knowing lift force, okay, how particle is spinning. In Euler you don't take care of this at all. You cannot take care of it unless you track spin of a particle. Typically nobody does that, okay. So spinning particles, and the spin is important. In Euler it is kind of challenging, okay. And interparticle collisions, again you have to use a model, in other words contact mechanics model, soft sphere, hard sphere. So there is modeling involved, but nevertheless you can take it from near first principle. You can check who is colliding with whom and what happens, etc. you could do, okay. So those are the advantages. And the disadvantages is it's not fundamental in the sense, what I meant by this is, yes, yesterday we derived the governing equations, that is fundamental, but you have to use closure models, okay. So in other words, that's what I meant, is that when you say Navier-Stokes, when you do particle resolved, of course even in particle resolved simulation there is model. If you have contact mechanics, you have to do a model for collision with the wall among the particles. People were talking about micelles, surfactants. There are other complexities come in, but at least just the motion of the particles and some basic fluid mechanics doesn't get affected. So there are models even when you do DNS, but on top of all those models now you have to use closure models because you are not considering flow around individual particles, okay. This is a disadvantage as compared to resolving the particles, but it's computationally far more affordable. You can track billion particles, so resolving billion particles is just not possible, okay. Requires, but also now you have to think how to interpolate fluid velocity. The last bullet is numerical. So far I don't talk about numerics per se a whole lot, though we talk about methods. All the equations, everything is the physics of the problem. I'm not talking about whether you use Runge cut or whether you use finite difference. Those things we have not focused on, okay. But here one issue that you have to do is when you have particles as Lagrangian and fluid as Eulerian, you have to think in terms of interpolation from fluid to particles, and then if you have two-way coupled and you have some heat transfer, some drag, you got to put back. Are you going to spread it over your cell, or are you going to spread it over the near 9 cells? Because your smoothness, etc. will matter. Imagine a situation where you are putting your force back and yours is a very dilute system, and grids may have particles and may not have particles. And now I ask you to go and plot the feedback force. You will have one cell will have feedback, another cell 0, another cell 0. That's very nasty looking forcing you are doing, okay. Numerically it may be very unfriendly, okay. Now, this is an issue you have to think. Earlier I said in Euler-Lagrange you typically want to have particles smaller than the grid, and at least several of them in each cell. The reason you want that is you will avoid, if there are 100 particles on average in a cell, that may be computationally difficult, maybe 10 let us say, okay. Then the fluctuation will be square root of 10. So, it could be 10 plus or minus square root of 10. That is the typical 1 sigma range. Okay. So, you can see 3 sigma is already 10 close to. Okay. So, there may be cells without any particles, and there may be cells with 20 particles. Okay. So, if they are all feeding force back, then that feedback force on your fluids may be spotty. Okay. For particles it does not matter because you are tracking individually, but when you feed back it becomes noisier signal, and it may affect your stability of your calculation. Okay. And the problem with big particles is this, because the feedback force is proportional to how big the particle is typically. Because what are you doing in your finite volume cell? Change of your fluid velocity there is due to advection plus diffusion plus pressure effects, right? Now, on top of it you have feedback force, that is an additional term. If that added term is not that big, even if it is fluctuating, it is not that big a deal. If that added term is big, if the particle's feedback force is very big compared to your advection and diffusion, it is going to change the fluid mechanics. And if you say one cell has a particle and puts a lot of force, and another cell no particle, you are going to have tremendous feedback force that you apply is highly noisy, it looks like garbage. Okay. And when you do the simulation and you plot your velocity, etc., it will look very noisy. Okay. Therefore, Euler-Lagrange simulations, you really want smaller particles, several of them per grid. Okay. Those are some general principles you want to follow in Euler-Lagrange scheme. Now, I want to now talk about, this is just a general scheme. There are 3 things, I am sorry there is a lot of things written in there, just only those that needed I will say it. The most important thing is how the particle and the surrounding fluid are coupled in terms of mass, momentum and energy. Since you are not resolving the flow, if there is evaporation, you must have a model for what is the evaporation rate. If the particle is burning, what is the burn rate, what is the drag, what is the heat transfer. They have that one kind of models. There are many of them, but this is one family of models. They all pertain to that point particle in a droplet or bubble interacting. So, that is one set of models that we need. The other set of model is pertains only to the fluid. Now, you are saying, okay, there is a cell average velocity, but there is fluctuation in fluid velocity inside the cell. This is what typically is called Reynolds stress. Reynolds stress in the temperature equation, U times T average will be replaced by U average times T average. Every quadratic term, average of a quadratic term is not available. So, you will have to write that as a quadratic term of averages, because we are computing only averages. That is, so I tried to explain what that means. People have asked for me to send the slides to you, and I will do that. I will put them in a shareable folder, and I will give you access to that. You will all go, these slides will be there. Okay. But right now I am saying just generally what is happening is sub-grid fluctuations in the fluid themselves, temperature fluctuation, velocity fluctuation, pressure fluctuations, etc., will matter, and they will give rise to what are called Reynolds stress like terms. Okay. You have to model them. Okay. If they are important, they need to be modeled. And the last thing is viscous term. Okay. This is what the Einstein's viscosity and other things that I was talking about. In other words, the stress in the fluid is not going to be that of pure fluid, it will be that of the mixture. So, you need a model that will tell you how viscosity and conductivity change with number of particles. Okay. So, Those are the three types of models you will need, and we will go to the details in the next lecture. Okay. Any questions so far?
So could you repeat about the feedback forces, which you say that the larger particles, depending upon the particle size, the feedback forces will vary. And when these feedback forces will be added to those advection, convection, diffusion, the flow mechanics will be changed.
Yes.
So sir, can you say that again which size particles, the larger size particles will have the bigger, feedback forces?
Yeah, because you see, Stokes drag, even if it's Stokes drag, is proportional to diameter, right? So one big particle will apply a lot of force, feedback force. Of course, you see, this is all loose talking. If that particle is just moving with the local fluid, then the force would be small. So the potential for a big feedback force, the main message that I want to do is, bigger the particle, feedback force could be large, and that feedback force could be a big component compared to your advection, etc. So you can't argue, oh, feedback force is small. Okay. So the next time step velocity may depend on that feedback force. Then you can see one grid where there is a particle, velocity will change in the next step, whereas the grid that doesn't have a particle will have a different velocity. You could have a very noisy velocity very quickly, right? So one has to be very careful. So in other words, we need also numerically some smoothness. Otherwise, you can have instabilities, numerical instability, not physical instabilities. So I was just in a two-way couple, in a one-way couple, no problem at all. In two-way couple simulations, be careful what is the feedback. The easiest way is, after you calculate feedback, you plot your advection term, you plot your diffusion term over your entire domain, you plot your feedback term, and see how they look, what their values are. Because if you finally got a gibberish looking flow, you got to go back and debug and say who caused it. Especially if you wrote your own code, it could be a bug. But if you use ANSYS Fluent or something like that, the code is good, the answer is looking bad, means there is something must have gone wrong. And you got to find, easy way to find is that plot every term which is on the right hand side of your momentum equation, mass balance equation, and you can see, well, what happened. Okay. And there you will find for big particles, and there are only few of them, you may see very noisy looking feedback force, and then it may be the root cause of a problem.
Sir, the same record, I have also one more clarification. Under what circumstances we have to consider a feedback force? Do we have any limit for in terms of volume fraction? But already oil and Lagrangian less volume fraction, dilute systems applicable. Can you know any kind of
Yeah, that's the thing. You remember in the previous lecture I was talking about, when mass loading locally, when mass loading starts, mass loading means the mass of particles that are in there divided by mass of the fluid. If that ratio is even 0.1 or 0.01, then the particles, just by the presence there, it makes the fluid heavy. Therefore, you have to do some two-way coupling. The other thing is that whatever I told her is another great way. Just assume two-way coupling, you put in there. Now you calculate your Navier-Stokes equation. So in ANSYS Fluent, you ask it to plot the advection term over a domain, you ask it to plot the viscous term, and you ask it to plot the two-way back coupling force term. You compare them. And if the back coupling is 10 to the power minus 3 or 10 to the power minus 4 smaller than the others, then that code itself is telling you it's not two-way coupled. It's not that big a deal. Okay. So two-way coupling is important only if that added force is comparable to everything else in your Navier-Stokes equation.
So another question. Sir, in this type of simulations, it is very important to see that who are the neighboring particles, right, sir? We have a particle A, then the neighboring particles, it is very important. So in this also, I mean, radial distribution function is only used to identify the, I mean, immediate particle neighboring, or there are some other good algorithms also to find out the neighboring particles.
This is for collision you're talking about?
Yes, sir.
Yeah, yeah. So for collision, one of the things that we have done is, irrespective, I think some of the codes do a good job. Answers for, if they have a DVM, they have. But the strategy they will follow is they will take the domain and bin it into boxes. And the box size will be such that a particle can move only inside the box. I mean, the size of one box. In other words, a particle in one time step cannot go from here to a box. You choose the box size in such a way that every particle that was in a box can at most be in the 9 boxes. The same box are the 27 boxes that are surrounding in 3D. So that it can move only within the box or out to the neighboring box. Then you calculate collision with every box, every particle in any box. You only have to check whether it's colliding with all the particles in the neighboring boxes. Okay? So this box doesn't have to be your grid. Typically it could be close to your grid, but it doesn't have to be. Okay? So this is the typical strategy people will use for collision detection. I have a paper with a guy by the name, my student David Zwick. It describes an algorithm, how to implement it, and it's been referred. It just appeared 2-3 years ago. In fact, I also have a code if anybody is interested in DEM approach, and it can be combined with any finite volume block structured grid. It can be combined, and I will be more than happy to share it with you guys. So he's a really good computational student. He wrote this code called PickleF. The software is called, and it's in GitHub, and I can give you access to that. And this is the strategy he used. He used this strategy, and it scales. He ran simulations on 100,000 cores. Okay, it scales beautifully. Okay, so it just so it's MPI, etc. So you could use it in any kind of computational system. So he tested it thoroughly. Okay. And what it does is it moves the particles, it does the interpolation from the fluids, and then it gives back to the grid, background grid, the feedback force. It detects collisions and does everything. Yeah. Did that answer your question? Yes. Okay. So the strategy he used is binned approach. Okay. And he also used some more sophisticated called overlapping bin structure, etc. to make the collision is the most expensive one. So he tried to make it as accurate, as efficient. In fact, he was trying to do this for a shock going over a dense packed bed. Therefore, a lot of collisions were happening. Okay, so many of you are doing fluidized bed, and this may be a good. In fact, he has a paper. Actually, he has 2 papers. One in supercomputing that describes the method, and he has another JFM paper that's very much like a fluidized bed problem he studied. Okay, so he used this code. So if anybody is interested, and it's also coupled with another code called NEC 5000. I don't know how many of you are familiar with this. This is an incompressible code, low speed. It can do LES, all sorts of stuff. So it's already combined. So you can do Lagrangian simulations in any kind of flow. If any of you wanted, this is all freeware. I'm really glad you brought this up, because this I should have been doing this. Don't send me emails how to use the code, please. That's not going to work, because I have never even seen the code. Most of the students deal with it, but I can put you in touch with students. But you may not even need this. There's an extensive document my student has written for the particle part. This is the Lagrangian part of the code. This is the Eulerian part of the code. It does DNS. DNS in the sense, not particle results. You could do particle result simulations, but PickleF does Lagrangian part. You can do the Eulerian part of the fluid. I highly recommend this. There are at least 300, 400 people using this code, individual researchers, very well tested code. But one thing I must tell you that this is not going to be as easy as Fluent, ANSYS Fluent, because there obviously it's a commercial code. They make it easy, front end and back end. But this is a versatile code. If you are interested, it's something that you can pursue. Any questions? So here I want to talk about dispersed phase governing equations. Again, I don't want to go through the excruciating detail. I'm regurgitating whatever I said previously, is that you have particle size, you have fluid scales. Okay, so there are particle size. This is nothing but interparticle spacing. There are a lot of fluids. You have a Kolmogorov scale. You go up to big eddies, and numerically you have filter scale and delta x and so on and so forth. Okay. So when you look at governing equations, you really need to think in terms of how big are the particles compared to Kolmogorov scale or the grid, etc. For the grid, you definitely want your particles should be smaller than the grid, but how big is your Kolmogorov scale? So in other words, the point I wanted to make in this one is that there is no one governing equation. You really have to think a little bit about where you are, because this also I said in my previous slides that with PR DNS, PR particle resolved or particle unresolved, LES, DNS, etc. So you have to figure out which regime you are in. Okay. In this slide, what I wanted to say was, if particles are small, this m dot, you remember, m dot is the mass exchange between the particles to the surrounding fluid. You can easily compute what it is from mass of 1. So in other words, if you have droplets 1, 2, 3, 4, 5, etc., and mass droplet 1 is evaporating, and you know the evaporation rate, you got to put it back in the fluid, right? All this red box is saying is that whatever this evaporating mass, you got to put back as a Gaussian, because that's the filter we used. So we have to be consistent, even though you did not, you start with some equation. The way you want to think is that m dot is the mass source on the right hand side of your gas phase equation. Where does that m dot for the whole cell is going to come from? This is m dot for a cell, whereas all you have is m dot for individual droplets. So you are doing a Lagrange simulation, you have a bunch of droplets, your cell has 10 droplets, and you know the evaporation rate of each droplet from your model. You have to now convert. This is what I was talking about earlier, that you have to couple the Lagrangian with the Eulerian. You only knew what's the drag of particles. Similarly, you only know the heat transfer of the particles, the models. You know the evaporation rate of the particle or the droplets, and the droplets are within the cell at varying points. Now you have to say each droplet has a Gaussian. So in other words, the Gaussian was the filter function, the coarse graining operator we did. Shouldn't we use the same thing to say, okay, this particle is here, it is evaporating, but its effect will be fuzzed out. That's all this says. There is nothing else. So in other words, this gives a very clean way of going from a particle level detail to what happens. How does it affect the fluid? Now, similarly, you will need to know the fluid velocity at the particle. There you will have to do the interpolation. Okay? So you have to keep those things in mind. Okay? When a particle is really small, it becomes easy. When a particle becomes as big as your grid, this red box is not that easy. Okay? That's why I was telling Euler-Lagrange is a good method. If the particles are small, then you can use all these kind of simple ideas. Now this Gaussian typically will be as big as 2 or 3 grid cells. And this is also very good, because I said that if you put all your force back onto only one cell and nothing to the next, it will not be a very smooth thing. But if you put back like this, every particle, even if it is sitting in this grid, most of it will go to here, but your Gaussian is little bigger. You're going to put a little bit here, a little bit there, a little bit there. So every neighbor also get a little bit. And also this Gaussian is centered about the particle. So if the particle is to the edge of a cell, you rightly distribute its feedback among all the cells in a very equitable manner, and you will end up getting a smooth feedback force. Nothing really crazy. Okay. So this is just I was just saying that if you look at the mass balance equation, mass balance of your gas phase, all the source terms now get summed up. Now, one thing, the Gaussian typically goes, so typically what you have to do is that you have to think in the reverse way. You want to know what is the mass added to a cell. Not only the particles that are inside going to contribute, even the particles are 1 or 2 cells outside will give you a little bit of contribution. So you have to do it. But you don't have to calculate what is the mass source here. You don't have to find a particle who is out there. So there's a little bit of bookkeeping there, and you can easily do this, and it works very well. Okay. Same thing here. So everything, so you remember I said there are 3 kinds of coupling: exchange between particle and the fluid. That's what I'm talking about. How to handle that. Okay. So how do you go from individual particle information back to feedback force to the gas phase? And for the energy, the same thing. So this applies for mass, momentum, and energy coupling between the particles to the surrounding flow. Okay. So this was the equation that we wrote. I mean, only the first 2 we wrote, but this is rigorously derived. This has everything in it, and several times I made sure there's no reason to compute all of these terms. It's just there. It's rigorously derived. This equation, by the way, if you use the perfect closure models, if you know all these closure models are sort of circled in red. Terms that are not circled, you are computing, you already know. So in other words, everything that's in red, somebody from outside must give you as a model. Richardson-Zaki model or heat transfer model, somebody must give you. Now, I want to make one strong claim. If those models are perfect, these equations are as good as Navier-Stokes. See, I told you 2 things. When you go from particle result to Euler-Lagrange or Euler-Euler, you make 2 errors. One, let's talk about Euler-Lagrange. You say, I am going to compute only large scales. I am not going to compute anything between smaller than my filter size. You say that outright. That loss is irrecoverable, because you're not going to compute, you're not going to be saying anything about small eddies. Now, so we all agree that in this case we are going to consider only average velocities of fluid in a grid. The question now is, am I doing that very well? Subgrids are lost. Eddies that are bigger than the grid are being computed, but you may make a mistake in computing them because you did not have all the small guys. That is where the closure model, all these circled terms are supposed to take care of what happened within the cell, subgrid. That's why I said if these models are perfect, then your Euler-Lagrange is perfect. Only thing it misses is all those small eddies. But whatever you're computing as good as you can. There's nothing you can do better. So in other words, the way to think of this is the real flow is in a trillion dimensional space. It's really complicated. When you do Euler-Lagrange, you are saying I am projecting it onto a much smaller space. That smaller space deals only with big eddies. What is not on that space is small eddies. The question now we are asking, that reduced dimensional space on which we are computing, am I doing a good job? In other words, I am computing only the large eddies, but do I do that correctly? The answer is yes, you can if you have a perfect model. Typically, the answers are not good because these circle terms are not correct. And that is why there is a very good reason why these circle terms, you need to make them as good as you can, so that your answer on the reduced dimensional space will be as good as it can. Okay. So, in these circle terms, I talked about, so let me use a different pen. This is the subgrid stress term. These green things are subgrid stress terms. And these are the Einstein's viscosity kind of terms. Because I said 3 kinds of models: red model, green model, purple model. Those are the things. Everything else is interface coupling. Okay. Now, there is a lot of detail that given in the book about every term. I have tried to say what people do, what people have done, when you need it, when you. So that is why the book is like few hundred pages. So I got to cover something. So I've got, and I don't think there is necessary for me to discuss it here. Okay. Now, what's the dispersed phase? You have these tracking of particles. Okay. Mass of the particle being tracked, velocity of the particle being tracked, angular velocity if you want you can track, and temperature. And the circle terms, in this case the circle terms are the same ones that appear in the other equation. Here Lagrangian information, each particle's heat transfer, each particle's mass transfer. This modeling you typically will do here, and you spread them using a Gaussian and apply them on the gas phase. The only other thing is the 3 green boxes here. These are the interparticle collisions. Okay. That if you do a DEM, you don't need to model it. I mean, you will model it as a soft sphere collision. Okay. But you have to, but there is a different kind of model. But this, since it is only talk between the particles, it never appears in the gas phase, because this is something between the particles, and by Newton's law it is equally applied and so on and so forth. So you have nothing to worry about. So that's the let's see if I have anything more. Any questions on that? Can I just spend 2 more minutes and then be done? I just want to say the following. Okay. Now I want to take, these are the equations that we wrote before. I just want to say this has all 5 effects: volume fraction effect, volume effect, inertia effect, gravity effect, viscosity effect, and slip effect. If so, this is your idea which you can throw away and make your problem simple. You don't have to use this equation all the time. Volume effect is, there is phi c all over this equation. If volume fraction is small for particle, phi c is 1. Everywhere you just set phi c equal to 1. Will simplify your equation tremendously. Inertia effect, what inertia says is, it's typically, I don't know how many of you know what is called Boussinesq's approximation. Okay, yeah. Boussinesq's approximation says in a fluid, in a single phase fluid, if density is changing, the Boussinesq's approximation says set the density to be the constant density everywhere except when it gets multiplied by g. That is what Boussinesq's approximation says. Now, non-Bisenex fluid, you have to take care of rho everywhere. So, here you see this rho f that appears here. In some sense, you can take this to be pretty much a constant. Okay? So, in other words, inertia effect is you really don't have to worry. In fact, when you set phi c to be 1, I actually misspoke. Okay? Let me be careful here. Let me clarify. Volume effect is setting this phi c to be 1. Okay? So, please erase what I said. I said something wrong. Okay? Let me go all over again. The volume effect is only phi c being 1 in this equation. In the mass balance equation, you say fluid is everywhere. Inertia effect is basically setting phi c to be 1 in these equations. So, in other words, you are saying, well, forget there is more particles there, it's heavier fluid, etc. Don't worry, it's just fluid everywhere. Okay? So, it's the same thing. It's basically both inertia effect and volume effect if you don't care about them. So, in other words, if your mass loading and volume fraction are small, if volume fraction is small, volume effect is negligible. If mass loading is small, in other words, the two-way coupling is not due to the fact that you have a lot of particles. Then, so this significantly changes. Body force effect, well, that's pretty straightforward. You ignore your gravity term. Okay, but gravity, that little term there, that's exact. I mean, there's no modeling involved, but it plays a big role in many environmental flows. In high speed flows, there is no time for gravity to make any difference. So, in some problems you can throw this out and not have to worry about it. Thermodynamic transport effect, it just has to do with modeling this term and modeling this heat flux and stress. Okay, what kind of viscosity you are going to use. And the slip effect is the most important one. It's causing mass, heat transfer, etc. If it so happens that your Stokes number is really small, this is what happens in some environmental flows. The body force effect, gravity plays a role, but the particles are almost going with the fluid. You can throw every one of these things, and all you have to do is take care of body. It just behaves like a convective flow. So, that is also a multi-phase flow, whereas in other problems like fluidized bed, where their gravity may be important, but change in viscosity may be not important. So, you have to choose. Fluidized bed actually is a hard problem, because all the effects perhaps are there. Okay? But in other problems, you can make considerable simplification. Okay? So, here is a simplified equation, much simpler than this is a multi-phase flow equation, a subset of the previous equation. Do not worry about the details. So, there are some specific assumptions I use: volume effect, inertia effect, thermodynamic effects. They are all 0 in this case. Only the slip effect and the body force are. Now, you can, the point I am trying to make is there is no one equation that I can tell you, Euler-Lagrange equation. They come in different varieties depending upon what you want to take care of. Okay. With that, let us stop.